Statics questions, one in which the system does not accelerate. The problem with that is that I chose examples that were very specific so that we didn't have to worry about what we're going to worry about today. Now, you guys are going to rate my drawing skills, so I should just not care, but I do care a little bit. So let's see how this goes. And because I did grow up in the 80s, a skateboard, right? The answer is yes, Mr. Sheldon. It looks exactly like a skateboard. There we go. I don't believe you. And remember, me moving your homework relies on me believing you. Thanks, birthday boy. Appreciate it. If it's just resting on a surface like it is, identify in your notes the forces that act on a skateboard. Follow your rules. We have rules. Paradise Falls, tell me one of the forces acting on a skateboard. You have to be more specific. In prior cases, it was easy to identify the normal force, but I see 2 points of contact with the ground. So pick one. So the normal force in the front or the back of the skateboard? So there's a normal force here, the front of the skateboard. Earth, give me another force. Okay, normal force on the back part of the skateboard. Winterfell, give me another one.
Gravitational force.
All right, so where would be best for me to draw that?
In the middle.
All right, so we'll assume it occurs at the center of mass of the object or the center of gravity of the object. So someplace in the middle. Anybody like to add any other forces here? That's disappointing. Because there are other things that are probably acting that you'd probably like to talk about. Yes, sir?
There'll be static friction.
Yeah, there's definitely going to be static friction here or here. It's the only way the wheels don't slide. Unfortunately, we only know how much there is, and there doesn't have to be static friction. Static friction would be there to prevent the wheels from sliding with respect to the ground, but if the system is on level ground, there might not be a frictional force there. Only when the object begins to roll will friction spring into action and start acting to make sure the wheels roll. So I think we can kind of narrow down our forces to these. Now, here's where things are going to change. If a person places their foot squarely on the sweet spot on the top of the skateboard, they could carefully make sure their weight was distributed on both of the wheels of the skateboard. Now, I'm going to make the assumption that most of you have stepped on a skateboard before, either successfully or unsuccessfully. It's likely your first couple attempts were unsuccessful. Those were the good old days, when watching you was more fun than it is when you were successful. But it is quite likely that you figured out pretty quick where you could place your foot and successfully push off on the skateboard without having a problem. And after a while, you probably learned more of the things you could do to manipulate the skateboard. Some of you probably becoming quite good at it. Most all of you learn to be able to kick up the skateboard. To step down on the back portion of the skateboard. And old skateboards had a lip on the back. I know a lot of the penny boards don't anymore, and long boards don't always have one. Older skateboards used to have one. Usually that and a kick plate underneath it, but I'm not sure they do that now with skateboards. But most of you recognize that you could step here and lift the front wheels off of the ground. Now, I've got like 4 kids who don't ever really write the right things down. They sit in the room, breathe in my oxygen, but need to make sure they're actually in this, because I'm going to call them out this year a lot more frequently than they're prepared. And the reason is simple. But here's where I want you to understand something. If you step on the back of the skateboard, will these 2 normal forces be the same?
No.
Is it plausible that this normal force can be 0?
Yes.
What condition would happen where that normal force is 0?
If you applied enough force for it to raise into the air.
That's right. When you step on the back, you don't make the net force unbalanced, but you can make the net torque unbalanced. I mean, the system can stay here, but begin to rotate upwards this way. What I want you to understand here is that up until this point, where you applied a force didn't matter, because we only looked at force and we reduced the entire problem to a point. But now that we understand there's this concept called torque, we need to be aware that there isn't necessarily a normal force, but several, and they respond based on where the other forces are. Yeah, to lift the front wheels, we need to figure out maybe how much force has to be applied so that this normal force goes to 0. That is a limiting factor. We can find out exactly how much force has to be applied there to lift the front wheels. These are statics problems, problems in which we take a look at how the forces and the torques combined to maintain balance. And the first problem we'll look at is a classic problem in most books. It's a bridge question. Sometimes it's a balance beam question. We're going to treat it like a bridge. They are the same question. The idea is that if it's a bridge or a balance beam, the bridge or beam itself is resting on a set of pylons, usually 2 of them. In a problem like this, generally, you can imagine the roadbed is coming out to the side and then it's cut away. And the roadbed comes up to meet the bridge. So the bridge has been put in place because there's something wrong with the road, or there's a river or chasm or something like that. Cars, when they enter the roadway, tend to drive across the pylons, like so. Now, I want you to think about this for a moment. At this moment, you should consider all the forces that are acting on the system. How many forces are acting on the system? Hold up a number of fingers, please. Don't wait until you see other people doing it. Looking around is waiting till other people are doing it. Interesting. All right, there are 4. Let's consider them all. There is the, I think, obvious weight of the bridge. How about the weight of the car? How about the normal force from the left pylon? How about the normal force from the right pylon? Now, some of you had 5. What am I missing? Yeah?
Wouldn't it be the normal force of each wheel of the car?
We could deal with the normal forces of the car's wheels individually. In problems like this, we're going to kind of assume the car is small or narrow when looking at the whole size of the bridge and treat them as acting as a single point. It doesn't change the problem drastically to separate it out to the individual wheels of the car. This is a bridge question. Now, before we actually work the problem out, I want you to consider that if the car was driving from right to left, it would pass these places as it went.
Why don't we have a normal force of the car?
We're not looking at the forces on the car, we're looking at the forces on the bridge. She asked, why is there no normal force in the car? That's because we're not looking at the car. We're looking at the bridge. Now, as the car moves from A to G, you should be able to describe for me when the right normal force is greatest and when the right normal force is least. Meaning, if the car is at A, will that increase the right normal force or decrease the right normal force? And as the car progresses across the bridge, how does that affect the distribution of the normal forces? I think most of you will agree that there's a place the car can be where the car's weight will be evenly distributed. Where is that? Sure. But I think also you'll agree that as the car gets closer to a pylon, that pylon's going to have to support more of the car's weight. Wouldn't that make sense? So in fifth period, we placed the car at C and worked the problem. In sixth period, we placed the car at A and worked the problem. I will let you guys decide between B, D, or F. They all have merit as to where we place the car.
G.
I will let you decide between B, D, and F, where we place the car. G is the same as A. So, you guys are awful. Thanks so much. Since the car's already drawn at B, I'm leaving it. F would be the same as B. The only one that would be interesting, perhaps, would be D. And that would be because D is at the center, but we already said it would evenly distribute the force of the car. So that's why I'd prefer to do it at B. And now you have a way of looking at how it changes as it goes from A to C by just checking out the other two examples. We will use the numbers that fifth period came up with. Fifth period came up with some pretty stupid numbers, but we'll go with it anyways. They wanted the bridge to be 10,000 kilograms, which means it's a weight of 100,000 newtons. They chose the car to be 1,000 kilograms. This is after their first number was 5. Not units, just the number 5. So you can understand why I'm a little frustrated. And that means it's 10,000 newtons. The following numbers I chose. The bridge is 100 meters across. And the pylons are symmetrically located 20 meters in from each side. All right? So we're going to solve the statics problem. There are some new pieces of information here, but there's also old pieces of information that are still true. The first is you can draw a free body diagram for this. If you drew a free body diagram, there would just be 4 forces, 2 up and 2 down. It's not particularly interesting. The net force is 0. It's a statics problem. The bridge doesn't accelerate, or at least you hope it doesn't. Now, bridges have accelerated before. It's usually been pretty bad. You guys, so net force is 0 here, But that doesn't tell us enough. This is why these problems change a little bit, in that there are two unknown normal forces that are both responsive. They change based on the conditions, which means we don't know them, and we can't assume for them to be the same. We know that they equal the weight of the car plus the weight of the bridge together, which is 110,000 newtons. I don't feel like I have to write it all out individually, say net force equals 0, and then solve. The upward forces have to equal the downward forces. We can skip to that, right? And if we can't, catch up. Now, again, this doesn't tell us how much each pylon is pushing on the bridge. For us to do that, we have to deal with the torques that these forces apply to the bridge. We have to deal with the fact that for the bridge to stay static, the net torque has to be 0. This is new and adds a bit of a dimension to this problem we didn't have before. Now, in order to do this part of the problem, I have an equation with two things I don't know in it, but you understand that that makes for harder math. Two equations and two unknowns. That's what we showed right here. So to kind of give us a fresh diagram here, because the other one was pretty full. And a free body diagram is no longer enough. We're going to draw, I'd say it's a torque diagram, but it's really just a way of helping us lay out our force. So I'm going to call it a torque diagram, and it's to help us figure out the individual torques, but there are some nuances here that are a little different. First, I will almost always make a torque diagram like this by just drawing something that's a straight line, a torque arm. Ultimately, you could draw whatever the shape of your object is and you'll be just as good. Then we should go through and identify where all of our forces are. We should draw them where they act on the object. You don't have to work on scale here. It's probably more important that you just make sure that you are accurate with about where they occur and the angle at which they occur relative to the torque arm. So I have two upwards forces. I have two downwards forces. And that represents all of the forces that act on the bridge. Now, this next part is going to seem confusing, I think, to a lot of students. I'm going to say it slowly because I think it's one of the most important things I'm going to say today. And I would encourage you to get each part of it down because some of it applies today, some won't apply until Friday. But in all net torque problems, we're going to attempt to identify the pivot point. Objects with a defined axis of rotation must pivot about that point. Objects with a defined axis of rotation must pivot about that point. Look, a wheel's going to have a pivot about its axle. It's that simple. So something that you know is spinning already has a pivot point. But there are two times when we don't know the pivot point. For example, if you just grab a stick and throw it into the air, it's going to spin. Now, it won't just spin about any point. Objects that have no physical axis of rotation will naturally spin about their center of mass. Objects with no physical axis of rotation will naturally spin about their center of mass. This was on last year's exam. which surprised the heck out of all of us. So we will have to address those kinds of situations. On the other hand, static problems, which have never been on the exam, which means this year's the year, static problems have the benefit, because the net torque is 0, you can pick any point as your pivot. Since the object doesn't actually pivot, any point can be your pivot for the problem. Objects that are static, that don't move, any point can be your pivot. I've said that, 3 times now? It is so important to understand this, because some pivots make your problem easier, and some pivots make your problems harder. So here's what you should do. You should always choose a pivot that eliminates one of your unknowns. Always choose a pivot that eliminates one of your unknowns. Now look, I want to take a look at this for just a second. And I don't want to spend a lot of time, but if I choose this point all the way over here as a pivot, seems reasonable. It's a point on the bridge. It's at the edge. I will generate a torque equation because I will add up all the torques and set them equal to 0. But there are 2 unknown torques. This just creates an equation with 2 things that we don't know in it. That's fine, because over here, choose my pivot point to be, say, here. Unfortunately, the torque arm now that I chose between the pivot and the weight of the bridge is 0. So I have eliminated that torque. But I know what that torque is. That's a known piece of information. Eliminating it means I have less information that I can use in my answer. That's usually bad news. On the other hand, there are 2 other places I can place a torque where I can eliminate one of my unknowns. I can place it here, or I can place it here. Now, I'll be honest with you. Even now, one of them is better than the other. But either one of them will generate one relationship. Our torque equations are always going to generate only one relationship. Torque is one-dimensional. For us, the axis is going to prove is one dimension. But this either eliminates the left normal force or both the right normal force and the weight of the car. One of those is clearly better for us. It eliminates 2 different things. Makes our problem super simple. But because I want 3 volunteers in a minute, we're gonna choose this, the left one, as our pivot. So I can force information out of 3 people, not 2. But this one would be better. It would be faster. I just want to make sure that I call somebody in the back table and somebody in the second to back table today. I don't know which side. The sticks will tell. All right? I just haven't heard from them yet. So our pivot is going to be there. In order to do this problem, we will need to determine the torque arm length for forces that are applied here and the torque arm length for the forces that are applied here. I will give you 30 seconds to figure out what these 2 distances are before I choose you to answer for me. Excellent work, everybody. So now here's the deal. This is how this works. Unlike force, where we tended to break our forces up into the x direction and the y direction, we won't have to do that with torque. But torques do have direction. But they're one-dimensional problems in most part. Meaning, we need to decide whether this is a positive torque or a negative torque. Now, your book has a convention, and I'm going to force us to use the book's convention so you have a better chance of getting the mastering right. The book wants us to always make counterclockwise or out of the board positive. Right-hand rule. Fingers curl in the direction of that torque. My thumb points in the direction of the torque. So counterclockwise out of the board. That being said, that's like saying that up is positive, right? The book always chose up to be positive as well. So the book is always choosing out of the board to be positive. I've said that 4 times, yet several people never made their pencils wiggle. Know that. Now, every single torque has 4 things that we must consider. Every torque is going to have, whether it's positive or negative, the size of the torque arm, the size of the force, and the sign of the angle. So, I tend to list the torques. So like the torque from the bridge, the torque from the right pylon, and the torque from the car. 3 different torques. We know they have to add up in this problem to be 0. It's a statics problem. The bridge isn't going to move. So we need the net torque to be equal to 0. Which means for each of these, we need to determine whether they're positive or negative, and then identify those 3 pieces. You've got 60 seconds to figure out this grid before I start calling you out. 60 seconds starts now. I'm going to start setting up. All right, so I think you should make sure you understand what I'm going to ask. You need to tell me, you need to fill in all those gaps and tell me whether it's positive or negative. We're going to start with Asgard Square. Who is that? Where's Square? Square's all the way on the ends? All right, Asgard Square. You can tell me whatever, any one as you want. You can choose the bridge, you can choose the normal force, you can choose the car. Which one do you want to tell me?
I will tell you the bridge.
All right, so start with the length of the torque arm for me, will you?
30 meters.
Excellent. That is the torque arm from here to here. So what is the size of the force?
100,000 ohms.
100,000. What is the angle between the torque arm and the force?
180.
Well, 180 would be this many degrees. So I'd have a force that way. So I don't think it's 180. It's this angle from here to here.
That'd be 90.
90. Yep. Is this torque positive or negative?
Positive.
So this torque causes the bridge to rotate this way?
No.
No. This torque causes the bridge to rotate this way, right? Are you having trouble?
Yeah.
Okay. Negative. Okay. Everybody follow that? Because now we've talked about it. Correct your work. Earth triangle. Tell me what I want to know. Pick one and fill in the blanks.
Alright, I'll do the last one.
All right, I'm ready.
So,
Torque arm.
it would be 60.
Excellent. Size of the force.
10,000 newtons.
Excellent. The angle between the force and the torque arm.
90.
Positive or negative?
Negative.
Excellent. Which leaves halo array. Anybody.
60.
So we look at, when I said anybody, I meant anybody at the halo array. Quick. I'm looking for how far away is the force from the pivot? Nope, the pylon's all that's left. It is. What's the size of that force? We don't know. That's right. That's what we're searching for. What is the angle at which it's applied? 90. And is it positive or negative? It is positive. Now, folks, that's the process of figuring out net torque. You now can add those up, set them equal to 0, and solve for the normal force, which I will do and finish this up. But I won't make you stay for that. I've done several. If I was to surprise you tomorrow, please have reviewed these a little bit. I am not intending to surprise you tomorrow. So when I add up all the torques, it's negative 3 million plus 60 times NR minus 600,000 equals 0. So 60 NR, you too, have a good day, equals 3,600,000. To find out what the normal force on the right side is, I just divide both sides by 60. And that's going to give me 60,000 newtons. Now, we know that the sum has to be 110,000. Taking that into account, that means the left side has to be 50,000 newtons. Interestingly enough, you'll notice that because the car is on the right pylon, it gets half of the weight of the bridge plus the 10,000 for the car, which is why it works out so evenly. You should definitely look at what you get when the car is over here at point A and what you get when the car is over here at point C, done in 6th period and 5th period. If this is my torque arm and my pivot is here and you push that way, what direction will this thing spin? Clockwise or counterclockwise?
Clockwise.
So it will spin this way, okay? In our problem, we are establishing that things that go counterclockwise are positive.
So negative.
So this would have